All right, so we're going to transition, from the midterm topics over to talking about how to expand the hypotheses we talked about into more groups. With t-tests, we talked about, comparing one sample to a population, comparing the same sample to itself with a dependent samples t-test. And we talked about comparing two independent samples with an independent samples t-test. So then the question becomes, well, what if I want to compare more than just two groups? What if I have more than two independent groups? Can I compare them all at the same time? So the topic today is one-way between groups analysis of variance, usually known as a one-way Anova. We'll talk about how we can think about comparing groups a little bit differently to expand it out to be able to cover more than just two groups at a time. So we're going to start off with like we had before, let's start off with an example problem. Look at, why can't we just do more t-tests? We already know t-tests. Why not just do more of those if we have more than two groups? Let's talk about the sort of the logic behind Anova and how Anova works, and we'll go through the calculations, and we'll talk about, there's going to be a bit of sort of an odd sort of strategy. We're going to talk about how you can't do multiple t-tests because they're problematic, but then we're going to come back around and talk about multiple comparisons, which are essentially t-tests that you do after an Anova. So it sounds contradictory, but it isn't. I guess it is a little bit. And then we'll talk about some of the assumptions, and then we'll talk about effect size with Anova, and how we look at effect size a little bit differently too than we do looking at independent sample t-test or any of the other t-tests we talked about. All right, so say you're working for a market research company and you're trying to determine, these competing brands of baby food, Beech-Nut, Del Monte, Gerber, and there are others. I just chose these three, and you're trying to figure out which one of these seems to be the most preferred by the babies that have to eat them. So this market researcher randomly selects 15 babies, and they randomly assign 5 babies each to try one of the 3 brands eating all the same food. So they use strain peas for all of it. So it's just the 3 different brands, but they're all doing strain peas. They probably pick strain peas because of all the baby food. It's one of the grosser ones, at least in my opinion. So if you could get a baby to eat strain peas, you're doing a pretty good job there. So liking here is measured by the number of spoonfuls the baby is willing to eat before they get upset, like cry or scream or throw the food or refuse to eat or whatever it is. So, the idea here, if they eat more of it, they must like it or something, or at least they tolerate it. Right. So 15 babies randomly assigned to 1 of 3 groups, and 3 groups being the 3 different brands, and then we start feeding them, see how much of each brand they eat. All right, so here's the outcome here of all the different, these numbers represent the number of spoonfuls that each baby ate before sort of refusing the food. We got the 3 different brands. We got their means, we got their standard deviations, we got their variances. So the question comes down to, okay, well, how do we analyze this? So to knowing what we know already, we can see that these are independent groups. They're in the same way that having 2 independent samples that are selected from a population and then randomly assigned to 2 different groups makes them independent. Well, because we're doing the same thing with 3 different groups, we now have 3 independent groups. Each has their own mean, their own standard deviation, and I just included the variances here too, just for the sake of sort of completeness. So knowing what we know now, the only thing we can really do is to try to do multiple t-tests. So knowing that we know how to do an independent samples test, I could take and just treat 2 of these groups at a time as my independent groups and compare them. So I can do Beech-Nut versus Del Monte, Beech-Nut versus Gerber, and Del Monte versus Gerber. So to add a third, to go to a third group, I'm now doing 3 t-tests instead of just 1. All right, so by adding just 1 more group, I've now tripled the amount of t-tests I have to do. And it gets worse. If we had more groups, it's not like adding each time you add a group, it adds another t-test. Each group you add, it sort of starts to exponentially sort of grow. I mean, maybe not quite exponential, but it starts to grow rather fast. So far, we've made comparisons between a single group population, 2 related samples, 2 independent samples. If we want to compare more than 2 independent groups, one solution here is just to do multiple independent t-tests. Okay, that seems straightforward. And with 3 groups, you'd have 3 tests. You got, if you think A, B, and C groups, you got A versus B, A versus C, B versus C. All right, doesn't seem that bad. You're now having to do 3 times the work. You're now having to do 3 tests instead of just 1. But each time you add more groups, it starts to grow rather fast. So if you had 10 groups, you would actually need 45 independent samples t-tests to compare all 45 groups. You're probably thinking, well, how is that? If you think about it, it's going to be, if you have 10 groups, it's 1 versus 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, 10. And then 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9, 2, 10. 3, 4, 3, 5, 3, 6, 3, 7, 3, 8. It keeps going. You actually figure it out. You'd actually need 45 different comparisons to be able to compare those 10 different groups. So that doesn't seem like a good idea, right? So now not only are we doing 45 independent samples t-tests, which seems crazy, because as we saw in the material leading up to the midterm, that just doing 1 t-test is sort of difficult enough. Now you got to do 45 of them on the same data. It seems. It's definitely not impossible, but man, it definitely seems like something I don't want to do. I don't want to do 45 t-tests, right? And the other problem is, not only is it sort of time consuming, and now you're doing all these tests, but each time you conduct the t-test on a single set of data, what's the probability of falsely rejecting the null hypothesis, right? What's our type 1 error, right? So that's 5%. Each test that we do has a 5% chance of getting a type 1 error. So if we assume the null is true and you conduct 45 tests, so you're doing 45 different t-tests, how many rejections will you have? By that I mean false rejections, right? So the null is true. How many times are we going to reject it by accident, which is a type 1 error? Well, with 45 tests, we're going to have roughly 2 to 3 false rejections, because if we take 0.05, my calculator here, if I take 0.05 times 45, it's, I don't know if you can see it enough, it's 2.25. Okay, so about 2.25 times. So somewhere between 2 and 3 times, you're going to get a false rejection. So we know that 45 tests, we're going to get probably 2 to 3, false positives. So that's not good. And this sort of goes back to when the very beginning of the session, we talked about looking at jelly beans and whether or not they cause acne. And they did like 20 tests, and one of them came out significant. It's the same idea that if you just keep doing tests and doing more and more and more tests, you're likely going to find a false positive just because of the sheer number of tests and the probability of finding those false positives. So we're now increasing the likelihood that we're going to make false positives, which seems bad. So multiple t-tests on the same data artificially inflate alpha. They don't really inflate it in the sense of it's increasing the alpha rate. It's just you're going to make more and more type 1 errors by simply doing more and more tests. So the problem with doing multiple t-tests is a few things here. So one is they're inefficient. So it's too many comparisons when we have even a modest number of groups. So it sort of lacks an efficiency. It's just sort of piling on more and more and more comparisons, which doesn't seem very efficient at all. And then the third one here, inaccurate, as we just talked about before, that multiple t-tests on the same set, you're going to get more type 1 errors, so that's not good. And then the middle ones, something we hadn't talked about, but there's a certain amount of imprecision in here. Because with 10 groups or even 3 groups, if there's a pattern of differences across the groups, doing multiple t-tests are not going to find that pattern. Because they're focusing on only 2 groups at a time, any pattern that goes across multiple groups is going to be lost. You're not going to be able to see it, to discern it, because you're just focusing on two groups at a time. It's sort of like, you know, not seeing the forest for the trees, right? Because you're focused so much on 1 or 2 individual trees, you're not seeing the whole forest, right? You're not able to see the larger trends, larger patterns. So what we need is a single test, so one test with one 0.05, right? Not multiple 0.05s, but one 0.05 that can compare all the groups together all at once and looking for overall differences among their means or between their means. And what we're going to use for that is something called an analysis of variance, which I have this capital letters because the AN, O, and then really VA. It's analysis of variance, which is oftentimes called Anova. And I don't know why, but whenever people say Anova, it sort of bugs me. So just Anova, right? Analysis of variance, Anova. And the reason why I think Anova bugs me is because it's not analysis. You don't say analysis, it's analysis. So it's Anova. Anyway, so this analysis of variance takes a slight tweak in our thinking about variance in general, and it's actually a pretty smart way of being able to compare multiple groups all at once with a single 0.05 alpha. All right, so if we're going to think about analysis of variance, we need to expand our use of variance. So when we actually think about variance, we define variance. So far, we really just thought about it as one thing. Like there's variance. We didn't talk about different types or different brands of variance or anything. We just said there's variance, and that's it. So when you think about, well, how can that be expanded? How can we think about variance maybe in a different way? So here's a basic variance formula we talked about before. This is nothing new, right? So our variance, and I mentioned it briefly before, but I'll mention it here again just because it's going to come up more often in this analysis of variance section, that oftentimes variance is referred to as mean square. And the reason why is up here you have the sum of the squared difference between the mean and each score. So this is a deviation. Each score is deviation from the mean. So this is the sum of squared deviations that we oftentimes refer to as just sum of squares, SS. So if we take the sum of all those squared differences and we divide it by something like n, it's actually n minus 1, but close to n, we're basically getting an average. All right, another word for average is mean. So at the top is the sum of squares. If we divide by degrees of freedom, we're getting an average sum of square, or a mean sum of square, or a mean square. So sum of square up on top, if we divide by degrees of freedom, we get a mean square, and a mean square is just another word, another term for variance. All right. So if we think about this for a second, one of the things you'll notice is that there's not a lot of subscripts. There are subscripts, but not a lot of them. We have that the mean has a subscript of x to tell me this is the mean of that variable. X has a subscript of I, which tells me that we're going to do that for each individual. That's what I is there for. Each individual person or each individual score is going to have the mean subtracted from it. And then n doesn't even have any subscript because it's assumed that we're talking about one group. Like, so when we first talked about variance, we were just talking about it in a sort of generic term because it's really referring to just one group of respondents or one group of scores. But we don't have to think about it as one group of scores. We can think about it a little differently. So looking at the data, we can actually, and we already did it before, we computed a variance and standard deviation, right, for each of the groups. We have a variance for Beechnut, a variance for Del Monte, a variance for Gerber. So we can compute each of these sort of separately. So going back here, this doesn't really indicate that, right? Because there's no way of differentiating between the groups. what we need is, some other subscript. What we're going to start doing is seeing that we can add in. So if I refers to individual, we can stick in, say, J, like that, J here, a J there, and a J there, to indicate that I have different variables or different groups of variables. So J could, J1, like if J was 1, that could be BeachNet. If it's 2, it could be Del Monte, and 3 is Gerber. So it's telling me that I'm going to have scores from different J groups. They're going to have a different mean for each group and potentially a different sample size. They could have a different sample size. All right. So I can now start to think about them as different in different groups. I don't have that. So now I'd have a variance for group J or a mean square for group J. And this then would be the sum of squares group J and the degrees of freedom group J. Everything now has this J subscript to indicate that it is for a different group. And because this has got the double subscript of I and J, it's talking about each individual in each group. This variance, could have, again, if J, this is J1, this is 1, this is 2, and this is 3, I can think of this is, X 1, 1 for being in the first individual in group 1. This is 2, 1, 3, 1, 4, 1, 5, 1. And this is the mean, the M for group 1, the mean for group 2, mean for group 3. So I can actually individuate which groups I'm talking about and be able to tell the difference. So those subscript will help to tell apart which groups I'm referring to when sort of calculating the variances when I have different groups. All right. So I can now have a variance for the BeachNet group, a variance for the Del Monte group, a variance for the Gerber group. But what other variances could we calculate? How else could we think about variances? Well, one of them we already have done. So when we did the independent samples t-test, we calculated the average. So we calculated a pooled variance for when we had two groups by simply weighting each variance by the degrees of freedom, summing them all up, and then dividing by a common degree of freedom. So what this says is I'm going to sum all the n's for each group minus 1, so degrees of freedom for each group, times the variance of each group. And then I'm going to divide that by the sum of all the degrees of freedom. So I'm going to sum up all the n's, and I'm going to subtract k. We haven't talked about k before, because again, we were only really talking about one or two groups when we talked about t-tests. So now when we get to Anovas, it could be 3, 4, 5, 6, 7. It can be as many groups as you like. So k is now just a letter we're going to use to refer to group. So anytime you see k, k is referring to the number of groups. So down here, I'm going to sum up all the n's, and I'm going to subtract k, which is the number of groups we have, because we're going to lose 1 degree of freedom per group. So what does that look like when we start doing this for this particular sample? So I need to take each of the degrees of freedom times the variance for that group. So the first group, the variance is 3.8. So I can plug that in here, 3.8, like that. And they all have 5, so we really could simplify this down, but let's just do it the long way. So there's 5 minus 1. The next one also has 5 minus 1 because it is the same size. It's got a variance of 2.5. And this one's also going to be 5. And this one's got a variance of 2.3. Like that. All right. And it says on the bottom, I'm just going to sum up all the n. Sum n. So it's going to be 5 plus 5 plus 5, and I have 3 groups, so I'm going to subtract 3 there. You remember when we did independent samples t-test, it was n1 plus n2 minus 2, because we had 2 groups. So now that we have 3 groups, we're going to add up all 3 of them, and subtract 3, because we're losing 1 degree of freedom per group. All right. So now we can work this out. My calculator. So 5 minus 1, so 4. Oops. 4 times 3.8. So this part here is 15.2. 4 times 2.5. So this part is 10. 4 times 2.3 is 9.2. So we're going to add up those. 15.2 plus 10 plus 9.2 equals 34.4. Yeah. So up on top here, we're going to have this equals up on top 34.4. And then we're going to divide by 15 minus 3, which is 12 down here. So dividing this by 12. So we take 34.4 divided by 12. You get 2.867. So the answer here is 2.867. So this now becomes a pooled variance. It's a pooled variance for 3 groups instead of for 2. And like I said in one of the last lecture videos about the independent samples t-test, the reason why we pooled them together is because, well, 2 estimates of the population variance is sort of better than 1. So with that in mind, then 3 is going to be better than 2, 4 is better than 3. So the more variance estimates we have, and the more we can pool them together, sort of average them, the better the estimate's going to be of the population. Okay, so using these 3 groups, we're able to find a pooled variance estimate of 2.867 based on these 3 groups and their variances. Now, we can do that by, find the variance for each group and sort of pool them together. But we can also just combine everything into one. So instead of having to compute 3 different variances and then sort of averaging them, well, we can actually sort of just do it all at one time. Like I wrote before, that where we had sort of xij minus the mean of xj. So this is each score in each group minus the mean of that group squared. I'm going to sum up everything, and I'm going to divide by n, which I think I mentioned briefly before, but n, big N, is total participants. So capital N equals, we've already defined, we talked about before that we're going to sum the little n's, n1 plus n2 plus n3. Well, that's what this is. This big N is n1 plus n2 plus n3 plus however many n's you have all the way to the last one. So we already have something that we define as the sum of all the little n's is capital N. And because we know that k equals to the number of groups, capital N minus k is going to give me that degree of freedom I need for the pooled variance. So I want to make this connection here that the pooled variance estimate we're talking about is the same thing as the within groups variance, which is the same thing as the mean square within group. And I'm going to come back, we're going to talk about that again, but just start to make this connection. What the mean square within group is that we're going to talk about for Anova is really just the same thing as the pooled variance that we had for our independent samples t-test. It's just being expanded to more groups. All right, so pooled variance equals the within groups variance. Those two are synonymous. They mean the same thing. And then we also often refer to this as the mean square within groups because mean square and variance are the same thing. So all 3 of these are sort of interchangeable and mean the same thing. Okay? So again, each J is a placeholder for the group. So this could be, all the subjects, subject I in group 1, subject I in group 2, right? So these are just a placeholder for the group number that you're referring to. And by doing this, we're able to sort of get the pooled variance in one estimate of variance as opposed to computing 3 different group variances and then averaging them. Right? So it's just doing it all together. It's like an inclusive approach. So that's true. What we need then is to figure out how this works. So I need each individual in each group minus the mean of their group squared over n minus k. Okay. So my first person here is baby. This first baby is this 3 year. So that is the first baby in group number 1. So that's x11. All right, so we'll start with x11, which is 3. Okay. And because they're in group 1, which is the beach nut group, that group has a mean of 4.6. So everyone that's in this group is going to have the same mean subtracted from it. So 3 minus 4.6, I'm going to square that. I'm going to keep going. The next baby is 4. 4 minus 4.6 squared. Next baby is also a 4. The next baby is also a 4. And then I got an 8. So 8 minus 4.6 squared. All right, so that takes care of the first group. All right, so I did x11, x21, x31, x41, x51. Did all the first group. But I'm not going to stop there. I'm going to keep going. I need all of them for the second group as well. So for the second group, starts here, number 7. I'm going to take 7, but instead of subtracting 4.6 like I did for everybody in group 1, I'm now going to subtract the mean for group 2, which is 6. So 7 minus 6 squared plus 4 minus 6 squared plus 8 minus 6 squared, 6 minus 6, and 5 minus 6. I'm going to keep going. Got one more group to do. So as I switch to the last group, number 9 there. 9, but I'm not going to subtract 4.6 or 6 like I did for those two. This has got a mean of 8.4. So I'm going to subtract out 8.4 here. And the next one is 6. And then 10. 8. And then last, 9 minus 8.4 squared. So not quite equals all of that. I'm going to sum all that up. And then I'm going to divide that by, well, I have 15 total babies in 3 groups. So it's going to be divided by 15 minus 3. All right, so that whole thing is going to be equal to the pooled variance. I'll just call this the, well, I'll leave it alone, the pooled variance for now. And we know that by doing this, we should be able to get all these numbers. It should equal that same 2.867 or whatever we had a second ago, 2.867, which is the pooled variance we found by sort of, yeah, 2.867. So let's see if that's true. So up here, I got 3 minus 4.6 squared is 21. So this is 21.16. 4, so that's 0.6 squared is 0.36. Right? 3 minus 4.6 equals, oops, 3 minus 4.6 equals 1.6 squared is not, what I just wrote down. I don't know how I got 21.6. I have to look at that like this isn't right. Must be something left over. This is 2.56. So again, it's also 0.36, 0.36. So 8 minus 4.6 equals 3.4 squared. This one's 11.56. Let's make sure I did that right again. Minus 4.6 equals 3.4 squared is 11.56. So keep doing this. This is going to be 1 squared is 1, 2 squared is 4, 2 squared is 4, 0, 1 squared is 1. So 9 minus 8.4 is 0.6. Oops, 9 minus 8.4, 0.6, 0.6 squared, 0.36. That means this is 0.36 as well. 6 minus 8.4, negative 2.4 is 5.76. 10 minus 8.4 equals 1.6 squared is 2.56. right? So 0.4 squared is 0.16. So we should be able to add all those up. So let's see, 2.56 plus 0.36 plus 0.36 plus 0.36 plus 11.56 plus, and we're down here, 1 plus 4 plus 4 plus 0 plus 1 plus, down here, 0.36 plus 5.76 plus 2.56 plus 0.16 plus here now 0.36 equals, so yeah, so all of this, when we add it all up, equals to 34.4. Now at the bottom we got 12. We know that 34.4 divided by 12 in fact does equal that number. Alright, so doing it this way is the same process. Instead of trying to find, you know, 3 variances and then averaging them, we could just put it all into one variance estimate altogether and be able to calculate the same pooled variance estimate. Remember, pooled variance, think of this as pooled variance, you know, aka the variance sort of within groups. The reason why it's called within groups is because the variance within groups is the average variance within each group. So we're taking the variance within this group, the variance within that group, the variance within that group, and we're averaging them. So we're getting an average within groups variance, which is why it's oftentimes called the variance within groups, which is also known as the mean square within groups, because mean square and variance mean the same thing. They're two different names. So I'm just trying to get you to associate those 3 terms together, because you're going to see them sort of interchange depending on where you see it, what book, what source. You're going to see it referred to by a different term likely. Mean square and variance mean the same thing, and in a sense pooled variance is the same thing as within groups variance. Alright, so we talked about, you know, this idea of variance in general, this idea of being able to find variances separately for each group, being able to pool them together. What if, you know, what if we ignored the groups altogether? So we know we have 15 babies, and those 15 babies were randomly assigned to different groups. But what if we ignore the fact that they're in different groups? We just treat it as one, excuse me, one large or larger group of 15 babies that weren't assigned to different foods. They were just 15 babies. That allows us to find, one, this sort of overall average down here, right? So this 6.333, so let's back up a second. The mean for this group is 4.6, mean for this group is 6, mean for that group is 8.4. But if I'm ignoring the group, I can find that on average, the 15 babies ate about 6.33333 spoonfuls of strained peas. And then get also this overall variance is 5.0952, which is just the variability across all 15 babies, ignoring the groups that they're in. So what if we ignore groups? So we can calculate something called the overall mean, that is called, or typically called, the grand mean, and the overall variance, which is oftentimes called the total variance. Why they don't call this the total mean and the total variance, or the grand mean and the grand variance, I don't know. But this is the grand mean down here, because it's the mean for everybody, ignoring group. This is the total variance, because it's the variance of all the babies, ignoring their groups, just treating them as one grand or total group of babies. So how do we go about calculating this and thinking about this in terms of the variance equation? So here, I want to compare this to the other one we just did. This has got the same thing in the first half. It's each individual in each group, right? So that's the same as it is back here, right? It was each individual in each group. But then we subtracted out the mean of each group. So 4.6 for everybody here, 6 for everybody there, 8.4 for everybody there. For the total, we're just subtracting the same single mean, the grand mean. Right? So instead of switching every time we switch groups, we're going to take each person in each group and we subtract out the grand mean. We're going to square that. And because we're only talking about one grand mean, this particular variance only loses 1 degree of freedom. One mean, 1 degree of freedom. Back here, there are 3 group means, so we lose 3 degrees of freedom. Right? So you can oftentimes think about, well, how many things do I have here? How many xij's do I have? Well, I have all right, n1 plus n2 plus n3. I have big N of these. Well, how many of these means do I have? Well, I have 1 for each group, so that's going to be, generically it's k. I have k of those, which is why that's the degrees of freedom on the bottom. For total, it's similar. Well, how many xij things do I have? How many total subjects in each group do I have? Well, I have capital N of those. And one, so right, remember 5 plus 5 is 5. I have 15 of those. How many grand means do I have? Well, I have 1 of those, which is why that's the degrees of freedom here. Okay. So for this, we're going to call this the variance total or the mean squared total. Again, they're the same. I want you to sort of see this. By the way, part of the reason why I'm overstating this, like these two things are the same, is I had learned, I had taken this 320 course, just like you are now. I had taken it when I was an undergraduate, and I did fairly well. I did okay with it, but I think a lot of it was I was just really good being able to memorize, the equations and apply them. But I don't think I really had a full grasp on what they were doing. Because when I got into the next course, which is like a capstone in stats, it used to be called 420, now it's called 485 US. We started talking about this stuff, and my 320 instructor referred to all the variances in the Anovas as mean squares. And then when I got to 45, they started referring them as variances, and it confused me. I had no idea. I'm like, why are we talking about like all of a sudden? I couldn't really. It took finally one day, like a light bulb went off. I'm like, oh my god, mean square and variance are the same thing, and it could have saved me a lot of time just sort of knowing that up front. So I want you to know it, so you don't go through the same, humiliating self-realization that these things are the same thing at some point. All right, so let's look at how this works. So we did one where we subtract each of the group means. This one we just had to subtract the same score, the same grand mean each time. So it's going to look fairly similar in terms of having all the individual scores from the different groups, but I'm just going to be subtracting out the same score each time. So we know that the mean is 6.33333. So I'm not going to write. I'll just go to 3 instead of to 4. So it's going to be the same in terms of I'm going to do every single score. So it's going to be 3 minus 6.333, right, squared, plus, the next one, I'm going to have 4, 4, and 4, each minus 6.333, and squared. Okay, and the last one there is 8. Okay, I'm going to keep going. Because now it's just one big group. So I need 7, 4, 8, 6, 5. 7, 4, 8, 6, and 5 are the next 3, right? 7, 4, 8, 6, 5. Then I need a 9, 6, 10, 8, 9. 9, 6, 9, 6, 10, 10, 8, and 9. It's trying to like a little easier. Minus 6.333. Minus 6.6.3 plus 8 minus 6.333 squared plus minus 6.333 squared plus. So you notice the first parts, the 3, 4, 4, 4, 8, 7, 4, 8, 6, 5, 9, 6, 10, 8, 9. Those are all the same as they were in the previous equation. The difference was in that previous occasion, in that previous equation, we were subtracting out the mean of each group. So it was like 6.4 and no. 4.86 and then 8.4? No, it's 4.6. I forget already. What were those means? We subtracted out 4.6, 6, and 8.4 each time. Right, so it was 4.6 over here, 6 there, 8.4 over here. For this one, because it is the total variance, our total sum of square here is actually going to be just the sum of all the scores around the 1 grand mean, this 6.333. So this whole thing we're going to divide by the total number of subjects. So in this case is 15. And so we're going to lose 1 degree of freedom for our grand mean. So we're going to be dividing by our 15 minus 1. And this whole thing, okay, is going to equal to our variance total. Again, just to reiterate, aka our mean square total. So those are the same thing, either or. Okay. So let's figure out what all these are. As tedious as it is, I think it's good to go through each one of them. And even on the video, what I might do, might be kind of funny, is to start it and then I can like speed it up. Just do it faster so it's not so tedious. But okay, 6 minus 6.333. Equals negative 3.333. I'm going to square that. So this is 11.109. Let's make sure I did that right. Minus 6.333 equals, yep, squared, yep. Okay. So anytime it's 3, are there any other 3's? Nope, it's the only one. 4 minus 6.333 equals 2.333. Square that is 5.443. So this is 5.443. So is this 5.443. So is this. The other 4's. This is also 5.443. I think that's it. Alright, so let's do 8 minus 6.333 equals 8 minus 6.333 equals 1.667. Square that. 2.779. So this is 2.779. So is this 2.779. This is also 2.779. Okay. Alright, 7 minus 6.333 is going to be like 0.667. 0.667 squared, 0.445. 445, and there's 7's. Nope. So, alright, so 6 minus 6.333 is 6 minus 6.333 is going to be negative 3.333 squared is 0.111. And this is also 0.111. Alright, we got 5 minus 6.333 equals negative 1.333 squared is 1.777. So this here is 1.777. Nope. So we got 9 minus 6.333 equals 2.667. 2.667 squared is 7.113. This is also 7.113. So the last one is 10 minus 6.333 equals 3.667. Squared is 13.447. I think that's all of them, so I'm just going to add them up. Alright, so 11.109. 11.109 plus 5.443 plus 5.443 plus 5.443 plus 2.779 plus 0.445 plus 5.443 plus 2.779 plus 0.111 plus 1.777 plus 7.113 plus 0.111 plus 13.447 plus 2.779 plus 7.113 equals, so I have that this whole thing here equals to 71.335. If we divide that then by our 14 here, 71.335 divided by 14 equals 5.09. So this whole thing down here is equals to 5.09. So down here I have 5.0952, and I got 5.0954 when I add it all up. I think that's because this is in Excel, and I had, obviously it was carrying to 4 decimal places or something like that. It's a little more precise, and everything here is rounded to 3, so it's really only trustworthy up to the 3, up to the 3 units that we are rounding so much. Beyond that, it starts to break down a little bit. So not surprised it's a little bit off. So 0952 that we have here, it's very close to 0954. Even though the 4 is off, it's selected because of rounding. All right, so if we were to round both of them up, 5.095, this is still 5.095. So we're getting around the same thing. Okay. I know it's tedious, but I want to make sure I go through all the tedious set of steps so you make sure you see exactly how it's done if you have to do it on your own. Okay. So we just found an overall total sum of squares divided by the total degrees of freedom, and it gave us a total variance that we have there, all based around this grand mean of 6.333. So we got pooled or within groups variance. We have a total variance. Are there any other variances we could compute? Well, the answer is yes. It's just not the kind of variance we're typically used to thinking of, because we think about variance as scores around a mean. So it's pretty easy to think about, individual group scores around their own mean, or one large group scores around a grand mean. But what about a variance between the group means? So what about how means can vary around a central mean? So instead of thinking about scores varying around a mean, why can't we think about means varying around a mean? Like, how far do these 3 means vary around the grand mean? All right. So I'm like, what? Because this is not something we've ever really thought about before. We had defined variance as deviations of scores around a mean. So now we're sort of taking that and expanding it out to being, all right, well, what about the variability of means around another mean? It's perfectly viable. It makes sense. It's just not something we may have thought about before to this, before to talking about this chapter, this topic. So what would that look like? Well, for a second, I want you to just ignore the n for just a second. So instead of thinking about it as the variance or variability or deviations of each score around a mean, I now have these 3 means, right? The mean of group 1, mean of group 2, mean of group 3. And I have that grand mean that we figured out before, which is the 6.333. So can't I just figure out what is the deviation mean, M1, M2, M3, around the grand mean squared? And because I have k groups, one grand mean, I'm going to have a degree of freedom of k minus 1. All right, so k groups minus 1 grand mean is going to be my degrees of freedom. And we'll talk about let's look at what this looks like and how it all goes together. But if I was able, if I'm able to do that, so take each mean, subtract the grand mean, square it, add them all together, I can figure out some way of getting a between groups variance. Sometimes variance between groups, sometimes just variance BG, and which also means it's also an MS, or mean square between groups. All right, so this shouldn't be too difficult. It's only 3 means after all. So that means I'm going to take my 4.6 minus my 6.333. I'm going to square that, plus my 6 minus 6.333. I'm going to square that, plus my 8.4 minus 6.333. I'm going to square that. And the whole thing I'm going to divide by my number of groups, which is 3, minus 1 grand mean. Now, if you go back to that equation for a second, there is this n right here. It says take the n of each group and multiply it in, which means this really should be 5 times this, right? 5 times that, and 5 times that. Right, so I'm actually going to multiply each of those square deviations by the number of subjects, number of participants. Now, it's written this way here with n sub j because in reality, and this doesn't apply for our particular example, but in reality you could have groups that have different numbers of subjects in each one. Right? This one could have 6, this one could have 7, that one could have 10. It just happens that our 3 groups, they're exactly equal, but it doesn't always have to be that way. Each group may have a different n, and you can multiply each time you're doing the deviation. If like this, if you may have an instinct or something, or your gut's telling you that it seems weird to multiply by 5 each time, you could factor those out. You could factor these out of here, take them out, and then sum everything together and multiply by 5 one time. Take the whole thing and multiply it by 5. That's perfectly fine too. It just, in the sense of changing to n, no subscript, because now we're assuming all the n's are equal, times the sum of each mean j minus the grand mean squared, right? Just so the n now just gets factored outside, but this only happens when if n1 equals n2 equals n k, how many groups you have. If that's true, then you can do this, and I'll talk more about that in a second. But for now, we can take 5 times each one, and that will work as well. Or you can add them all up and take, actually, let's do it both ways. You can see that they're both the same. Okay, so 4.6 minus 6.333 equals. All right, so inside here, this is, I gotta square it. Squared. This is 3.003. So this, here, I'll even write a different marker. All right, so let's do, go back to pink. This is, inside here is 3.003. So 6 minus 6.333 equals negative 0.333 squared. Inside here is 0.111. 8.4 minus 6.333 equals 2.067 squared. 4.272. 4.272. Okay. Now, if I, so this is all, these are all before being multiplied by 5, right? So up here, I'm gonna multiply, take each one of these and multiply by 5. So up here is going to be, 5 times each of those things, each of those. All right, so this is like the 5 times row this way. So 3.003 times 5 equals 15.015. 15.015. 0.111 times 5 is 0.555, obviously. 4.272 times 5 equals 21.36. If I add those up, 15.015 plus 0.555 plus 21.36 equals, I get 36.93. All right, and we're going to divide that by, oops, forgot that was there. I mean, it's not right this here then. So we end up getting then down here is the sum of squares, degrees of freedom. We get 36.93 divided by 2. 36.93 divided by 2 equals 18.465, which is really close to this. Okay. What if I did it the other way around? What if I first add these up and then multiply by 5? So I'll keep that in pink. So, so 3.003 plus 0.111 plus 4.272 equals, so if I add all those up, all right, so this plus this equals, it's 7.386. If I then multiply that by 5 at the end, times 5 equals 36.93, which is the same thing as that. Okay, so whether I multiply each individual number by 5 to get these numbers here in blue and then sum them, or I sum the values up, multiply by 5, I get the same answer, but that's because n1 equals n2 equals n3. All right, we can do it either way. We have flexibility. If the n's were different, you'd have to multiply each one by the different n and then add them up. You'd have to do it in that order because there's no common n with which to multiply at the end. Okay, so again, it's off a little bit in the decimals because of rounding and stuff like that. Because one of the tricks that often you're not told or whatever, going through any math or stats course, is that if you got to think about how many decimals you want to round to in the end. So if I want to have 3 decimals at the end, right? If I want to be able to round to 3 decimals, the only way to get any sort of accuracy rounding to 3 decimals would be that every step along the way in the problem, I'd have to carry to 4 decimals, like 1 decimal more than what I want to round to at the end. So because I'm rounding to 3, really only the first 2 are super accurate. The third is sort of wishy-washy. The fourth is really awful. All right, so I should have carried more decimal places than I want to round to at the end, and I didn't. So it makes this, a little bit, a little suspect. But again, if you were to round to 2, so we carried to 3 and we rounded 2, it'd be 18.47. That would be 18.47. That'd be the same. All right, so it's a little bit off, but let's just do it a rounding. All right, so that is, this whole thing, which I didn't write down, this whole thing is this is now the variance between groups, okay, also known as the mean square within groups, between groups. Okay. So with these three groups of babies, we now have three different kinds of variance we can play around with. So what does that do for us? How does having more variances solve any problems? It just seems like now we're just doing more variances, more deviations, more squaring. It's just more of the same stuff. How could that possibly be a solution or be helpful in any way? Well, let's figure out how that might help us.